ER4120, Computational Mechanics, Numerical Integration, and I'm Dr. Whitty. So just to recap on last week, we saw that if we have what we call a linear model where the linearity is implied by the matrix, so we could still have try to do a polynomial fit to the model, though the linearity is within the matrix itself. So we have a set of data points, readings, y1 to yn, from a set of x values x1 to xn, and the idea is to get the best values for the constants. So for instance, if this was a linear model, we would only have x1 and 1 and x1 in the matrix A, and it would still be known as a linear least squares model in this sense. So we saw that it was an optimization technique in which to optimize the empirical error when compared to the polynomial model, and we looked at linear models last week, where we had ones in this slot, x, and then our x values in this slot, and we were to work out b0 and b1, for instance. And we saw that for a generalized system, the idea was, well, if this is a rectangular matrix, the only way in which we can attempt the problem is to make that matrix square, so we can invert and try and find b, and we found that if we multiply both sides by the transpose of the matrix A, we would get a square matrix which we could then invert, or better still, we would solve by either Gaussian elimination or Gauss-Seidel methods, depending on which one was more optimal. So in a previous example, we showed that it was important to have knowledge of the underlying physics before conducting any interpolation and or regression of empirical data. And we looked at exploiting linear elasticity, not expecting any stresses or residual stresses in a perfect specimen. And here we have a particular research problem within the John Tyndall Institute, which is concerned with the fatigue characteristics of composite materials, a number of projects in this particular area at the moment, it being assumed that the mid-cycle life is an adherence to the following, what we call linear fatigue model, for reasons that will become obvious momentarily. So with a failure stress of the component raised to a power multiplied by the number of cycles to failure is equal to a constant, is the model. And we have some data here that says the number of cycles to failure gives us the failure stress. This is affectionately known as the SN data, where this is the stress and these are the number of cycles. And these number of cycles are per 1,000 cycles. So here we would have S to the 2,000 cycles, we would have 441, and as you move up to 1,000 cycles, 1,000,000 cycles, you're looking at 86 megapascals. So the fatigue means the material gets weaker with the number of cycles. So given the nature of the phenomenon, plotting these does not present any obvious relationship. So if you was just to plot, as we've done on here, 1,000 cycles, again, we get some type of scatter. However, if we look at this, we could take logarithms of both sides, and if you do that, we get something that resembles a straight line. This should take you back to your elementary mathematics, pre-calculus mathematics, or indeed your first year or second year maths on your degree courses. So the Python methods to achieve this, there are two methods available, generally speaking. There are others, but the two which are used extensively would be first just to apply the formula which we've developed, and or essentially use the optimize least squares functionality within the Skippy library. So the first is to enter the data. So this is simply entering the data within columns. I've then set up a ones, so the ones vector, which is requires ones and a tuple of two numbers, the number of columns and number of rows, quite simply. And then I've stacked these ones on top of the logarithm of the zeros. So essentially we have put ones and x1s, the ones and the x's, and then we've taken the log of the result, the log of the y values I should say, so the log of the readings, and stored that in y, and I've then asked it to solve. So I would have had to invoke the numpy solve as Skippy solve from the library before executing this, of course. So B is equal to A transpose A, which is the A matrix, A transpose Y, which is the Y matrix in this particular case, and therefore solving that would render the solution to the underlining linearization, and then thereafter we simply adjust the values of the slope and the constant, the first one being the constant and the second one being the slope, in line with these observations that the slope is minus 1 over m, and that makes sense because it's going downwards, and then a is equal to 1 over m. So back to the basic A-level mathematics. Okay, and the other way to do it would be straight out of the box, generally with the Skippy, remembering that you could just simply put in this function, s to the n, number of cycles equals minus a. However, for some reason I haven't got it to work. So I've helped the solver along, as we know how to do it. Again, a little bit of knowledge of the maths and the physics helps us along as engineers. So in this case I've simply got a, and I've reminded myself I need the log of n, the log of s, and I've just taken logarithms of this verbatim. So this would be the m times the log of s plus the log of n equals the log of a, and I've simply taken the a over the other side because I need this function to be the residual to be able to use the least squares. I'll then give it initial guesses of two ones, no reason for that, and then I've simply put through the arguments. The argument for Sn is of course the first, that log to the base 10 of the first column of data and log to the base 10 of the second column of data, and then I've simply adjusted the final value of AO by taking the antilog or raising the value to the power 10. Plotting these, relatively easy to plot. The first thing to remember is that you're now in log space, you're not in linear space. So I have set up a log space from 3, 6, 21, and if you look at that, that will put it in terms of, though I have plotted here on a linear scale, I've set up the variable, the x, the abacusa, as in log space. And then I've simply got s, which is a lambda, given a, which will be, we'll see in a moment, are these quantities, n, and then I've said an, so I've literally just applied this formula by reducing this by, and then taking this over the site, so I get a over nf, and then raising it to the power of 1 over the index. And then I've asked Python to plot each of these solutions over the top of each other, and we get very, very good results. And additionally, we can plot these to look at any differences on a log-log plot, which is done in this part of the slide here. So this we've just simply plotted again the data, but on a log-log plot, which gives us something resembling a straight line, and definitely straight lines for both the analytic and numeric. Again, very close. However, a little bit of data science. If we zoom in on this particular bit, you can see here we see the gradients are very similar, but presumably due to the initial guesses, then the constant values, the intercepts, are a little bit different when computed through the exact analytic method in this case, and the numerical optimized least squares resident within the Python SciPy libraries. So just to remind you of the teaching and learning philosophies on the module, it's roughly divided into 3 parts: the mathematical principles, which will concentrate on the solutions of ordinary differential equations. Solutions to partial differential equations take up the second part of the module, and it's interdispersed with research-informed case studies, which are basically based on work that's come into the John Tyndall Institute from industry, or indeed colleagues from other universities have asked us to solve problems using usually the ANSYS software, where we've had to underpin our solutions to these problems using either the solution to ordinary differential equations or partial differential equations. Teaching, the online lectures will be about 2 hours a week. These will be underpinned by 2-hour seminars and modelling tutorials, which I would assume at this particular point would be just related to answering questions based around these online lectures. Related to the teaching, of course, is learning, the self-study aspects. I would say coding and the completion of the tutorial sheets at master's level would take about 2 hours per week. The forthcoming assessment preparation, assignment preparation, will take about 2 hours a week. Revision and recitation, at least 15 hours a week to obtain a bare pass. If you're looking for a 2-1, then probably about a 2-2, probably about 30 hours, 45 for a 2-1, and probably a little bit more for a first class or distinction level marks. Probably looking about 90 hours for those distinction type and first class honours type, on top of the nominal workload of the module. Assessments are generally fortnightly worksheets which can be self-marked, and these will be the subject of the aforementioned seminars and modelling tutorials. So the coding tutorials, the extra 2 hours, will be related to completion of these fortnightly worksheets. They can be self-marked, of course, because we will be posting solutions, but if you do want some feedback, please do consider sending those to us by email. There will be a midterm on the 16th of January to the 17th of January, open for 24 hours, and I tend to leave that open a little bit longer for people, probably over the entire weekend, as officially it is formative, though it does cover all the learning outcomes for the examination, so can be used if anybody were to not do so well in the examination. This is a fallback position where we can say the learning outcomes have been met for the examination component. There's an assessment for learning, more about that strategy, and as we move into the assessment period, which starts in November and moves through to February. You would not be expected to be able to do that assessment straight away. It will be drip fed through these video lectures and accompanying seminars. The final exam at the moment is scheduled for the 21st and 22nd, that is to say the Friday and Saturday, the final day of the examination period in May. This is because usually students like lots of revision time on this particular module to prepare for the final online examination. So just reminding you of the overview of semester 1. We're just coming to the end of our preliminary mathematical underpinning, where we've completed interpolation and extrapolation. You should be finishing off the differentiation part of the first worksheet, and we'll then move into numerical integration this week and in the seminar next week. The modelling of ODEs again starts next week, when we'll look at first order and higher order in the first couple of weeks, transform methods, and then followed that a couple of weeks of transform methods in fact, and then we'll cover non-linear ODEs for a week. We'll then be in a position to release the friction heating assessment, and then move into Fourier analysis to complete the first semester. So just to remind you of the structure of these video lectures, you should be used to this by now. These are generally divided into 4 bite-sized parts. Firstly, I'll introduce the material recap and introduce the concept of numerical integration. Thereafter, we'll look at the concepts and principles used in quadrature, which is a archaic name of computing areas, and then we'll look at some particular computation examples of why these are used to evaluate integral functions, particularly associated with heat transfer and friction heating. I wonder why. And the summary and feedback, of course there's our usual formative assessment via the homework tasks, where they can be self-marked, or alternatively you can gain feedback from the team, and then possibly next Wednesday or next Thursday before the workshop sessions, do have a look at the learning survey for us. So just as a point of order, I want to finish off simultaneous equations. This is an aside, and just to look at what happens if we have overstrained equations. We've already done this when we looked at least squares, but I just wanted to look at this a little bit more formally. So here we have 3 equations and 2 unknowns, and the question is, how does one solve this? So we have 2x plus 3y equals 9, 3x plus 2y equals 6, and 2x plus y equals 4. Under normal circumstances, I guess you wouldn't know how to solve this, but now you have the tools in your arsenal in which to do it. If something's not square in linear algebra, the idea is try to make it square, and that does drop out from the least squares proof that we did last week. So to make something square, you can a rectangular matrix square, simply multiply by its transpose. If this was then done, because you've multiplied one side by its transpose, you have to multiply by the other side by its transpose, and then you would get the values for x and y. And in this particular case, you would say that these are solved in the least squares sense. Python least square solutions. Just as with curve fitting, one can do this directly using the usual solve command. So I've imported numpy into as np for short, and then from the numpy linear algebra library, I'm just going to import solve, so we can use it holistically as solve. Again, I've put the A matrix in. I've done that in the nominal way, in between square brackets. I've then put a list to represent each of the rows in the matrix. So, and then I've put a column matrix B together, and then I've just said, well, this, because I've got a square matrix, I need to solve A. This is A, so it'd be A transpose would be the A matrix, and A transpose times B would be the B matrix, if that makes sense. So in this particular case, we have this is the matrix and this is the column vector. An alternative method and probably a more direct method, or certainly looks direct. In fact, the method does have this under the previous method underneath it. However, you can simply invoke the least squares solution from the NumPy linear algebra. So instead of using solve, we just use the linear algebra, the least squares, which says solve the problem in the least square sense for me. So import NumPy as normally from NumPy linear algebra, this time lst square, which means least squares, and then we say A is equal to the same matrix as before, B is the same matrix as before, and now there's no need to use these transpose, it's just A, B. You'll find it either puts it as a tuple or as a NumPy array, and the values are given in the 0th slot of that, but you can find that from the help of the least squares. I think it puts it as a tuple. One of them are giving some type of error estimate because it uses a numerical technique. Okay, there are other methods of doing this, of course. It can also be done in Maxima and also in MATLAB. And here's another example of that. Of course, in Python it would be very straightforward now just to change the A and B matrix to these and use what went previously, but here we're just going to use Maxima quickly. So I've set up an A matrix, which is put this into matrix form. Important that it is put into matrix form, but very easy to do, of course. You just take the coefficients, and the thing to remember here is the -8 goes here and a 0 goes there for y. So that's where people do slip up, myself included, when putting these into the codes. And I've still got y is AB is what I need to put in. So I'm going to say A transpose AB is equal to A transpose Y, and in Maxima I just set up the A matrix, I set up the B matrix, and then I've just computed this by saying, well, I could take this over the other side and make it the inverse matrix. So it's A transpose A inverted in Maxima to invoke the multiplication of matrices is a dot, the transpose of A times B. In Scilab and MATLAB, this could be done again by inverse of A. Apostrophe is the transpose operator in MATLAB and Scilab, so A transpose A multiplied by A transpose B, or simply just invoke A \B, because what it will do, it will go through its nominal search criteria in Scilab and MATLAB to say, well, first and foremost, what's the most efficient way of doing it? Does a calculation see whether it should use a Gauss-Seidel method or Gaussian elimination? Solved by Gaussian elimination if it's because that gives you the exact solution. By Gauss-Seidel method if it's over, but of course in this particular case Gaussian elimination is trivial, and if the Gaussian elimination is not available, as in this case because it's an over-constrained system, it would resort to the least squares method, and if you look in the code you'll find that it actually just applies this formula. Okay, on to the learning outcomes for this session. Some of the work, especially on Gaussian quadrature, I've got from a different text, this time numerical methods for scientists and engineers, or engineers and scientists I should say, using MATLAB. and this is CRN press, though, and I've converted most of that across to Python. So after the session you should all be able to do parameterized engineering fatigue data. Well, hopefully you can already do that, or you're quite confident you could have a go at that. There will be an example within the workshop. Solve over-constrained systems of linear equations in the least squares sense. Well, we covered that in the point of order moments ago. Use computational tools to evaluate a wide range of antiderivatives. Now, when I talk about antiderivatives as opposed to integrals throughout this work, antiderivatives, I'm really talking about the fact that we have got a function as opposed to an integral, which is kind of used in both sense, but really we talk about areas under curves when we talk about integrals. So just antiderivatives is probably a little bit more exact for finding integral functions. And we also should be able to use software by the end of it very, very quickly. Use software to evaluate integrals using the very powerful Gaussian quadrature methods. So finally, I'm just going to introduce how to find antiderivatives. Now, most of you would have found integration harder in your undergraduate work than differentiation. There are numerous methods out there and a lot to remember, and I must admit I tend, if I have to resort to integration for any reason, I tend to pull a book off the shelf and look through that to find out what method what method is best by looking at the patterns of the functions which I'm trying to integrate. However, these days, fantastically, we have a Python. And this one of the reasons we've moved over to Python is there is a symbolic toolbox available called SymPy, SYMPy, which can be used to integrate and differentiate and do all sorts of clever things. You could probably find that in general finding integrals analytically, as I said, is more difficult than derivatives. However, when you use something like SymPy, it's just as easy as differentiation, which kind of gives it that added advantage for my liking. So an example here, something very simple. To integrate this function, we would just add, it's a polynomial, so you simply add 1 to the index and then divide out by that index. And with the added caveat that x, if you just see an x, we have to interpret this as x to the 1, and we interpret constants as 6x to the 0, so that's why constants disappear, because anything multiplied by 0 is, of course, 0. So in this particular case, but we're integrating, of course, so in integrating, this is why you would get a 6x back, and then, of course, you get plus a constant, because the constant would disappear on differentiation. I should have said that. So here we'd have 2x to the 6 divided by 6, so that becomes a third x. And then this would be x to the 3 divided by 3, and the 3's would cancel. And this would be x squared over 2, so the 2's would then cancel. And then we get 6x plus a constant. So that one would be straightforward. Hopefully you could get to this one, because sine becomes a cos on differentiation, so reverting backwards, a cosine would just become a sine. So we'd have cosine, and we've also got this 3 to take into account, which if we differentiated we'd have to multiply out, and because we're reversing the process, we have to divide. So that's what 1 over 3 sine. Sec squared might be a little bit more difficult, probably have to revert to a table. I think if I was where you were in my master's degree, I think I'd revert to a table to try and find sec squared. I think it's tan, to try and find the integral of that. Actually it's, yeah, I think it's tan. And this particular one is integration by parts. It's because it's a product. And in fact I've got us out the brown stuff here by not putting the dx there, and if since it's not there, the dx, then the integral is 0. So that was purposeful, just so I could mention that. If there's nothing to differentiate, you're essentially saying this is differentiated with respect to 0. So integrated with respect to 0. However, it's straightforward within Python to do this. We simply say from SymPy import symbols and integral. So these are the things I'm trying to integrate, and so these are I want to set up a symbols and use the integral function later on, and then from SymPy import the cosine, sec, exponentials. So these are the symbolic versions of the things in NumPy, for instance. X is equal to sims, and then in inverted commas, or between single quotes I should say, it's equal to x. So that sets up x as a symbolic. And then I've just simply said integral. Now this sets up the integral, as you'll see in the when you run these, it just sets up the integral, says okay, this is the integral, so this sets up an object called an integral of this ilk. And if you want to do it, you use the method, and to use a method in Python on an object, it's always a dot command. So we say dot do it, and then it would produce the result of that integral. And finally, in the final thing, I've got the exponential of 2 to the x cos, and I've just said do it, so don't show me the integral first, just do it straight out the box. So that's how to use, very, very simply, how to use SymPy, and there's plenty of online help in the SymPy. Just Google SymPy and it will take you to the relative site. A lot of people do really like things like Maxima for this, because it shows the symbols in a very, very mathematical, in a nominal mathematical way, especially if you use the front end WX Maxima. So here I've just simply asked it, I've put an equation, an example 1 here for instance, and showed you how to do that in Maxima. And of course it's always worth using Maxima and SymPy together for verification purposes. So the first of these examples is just to compute this integral, and we should all know this is e to the -2 over -2, and then I've asked the integrators will assume that the constant is 0. It's just going to give you the antiderivative to find the full integral. And there's the difference now between the two, I guess. Is you would need to add the constant, in this case I've called the constant C1. Here we have an ordinary differential equation for the first time. And we'll be doing more on ordinary differential equations as we move forward, probably from next week. But this is, we know dy dx, and we want to find x sine x, so we need to integrate both sides to get rid of the dy dx bit. It's just an antiderivative in that case, and but notice here we'd have to integrate by parts. But of course, straight out the box, Maxima will do this for us, and of course SymPy would do this for us if we set it up in SymPy to do that. We have to do a little bit of work with this particular problem when we set up the integral, and the way in which I've done this is I've set up the integral as two integrals. So I've done something called separation of variables, just to remind you of your, we'll return back to this next week, but I need to get my y's on one side with the dy and my x's on the other side with the x. So I've said this is y squared over dy, and I'm going to integrate that with respect to y, and this little apostrophe, single quote, means just set up the integral for me, don't evaluate it, show me what it looks like if you wish. We call it a noun. Rather than an adjective in Maxima will do the command, a noun will show you what it is about to do, or set up the equation for you so you can look at it. So we have dy by dx, y plus 1, so this would be x squared over this on one side, and then we would have x, 1 over x, integrated with respect to x. And this is also to remind you that if it's 1 over x, you can't then put it up to the top and use a minus 1. This is the caveat. If x is equal to minus 1, then the rule for reversing the process doesn't work. And you'll always get into trouble if you try to do it anyway, so don't panic. If you get into trouble by doing that and you have a division by 0 anywhere, then the answer is always the natural log of x. So that's the way in which to remember that. Though obviously that would have been proven to you in your basic mathematics calculus in the first year of your degree programs. To evaluate the integral, so I've set this up now as an equation C. To evaluate equation C, I've said the solution to 1CI is to evaluate this comma nouns. So that tells Maxima to evaluate whatever I've stored in this expression, evaluate the nouns which we set up, in this case evaluate the integrals. And finally I've made a substitution when y is equal to 2, x is equal to this, to find what we call the general solution. And I've used something called, I've then said, why don't you have a look in the workshop if you then did log contraction. It should give you a better form of these. So each form within Maxima and or SymPy are looked on as different values, even though technically they're the same answer. And of course you can ask SymPy or Maxima whether the expressions are the same by using the true command, double equals. Okay, just a moment to take care. Since the process of differentiation essentially makes a function simpler, polynomials reduce in order, then so long as the function is smooth enough, then the gradient function can be expressed in terms of so-called primitive functions. I mean, one way of looking at primitive functions are functions like sine, cosine, e to the x, sine, cosh, even though sine and cosh have more primitive functions because they're described by e to the x. Natural log is a primitive function. In contrast, integration produces more complicated functions, and the way to think about that is we increased the order of the polynomials when we looked at the functions that we've just integrated. They became more complicated. This means the resulting functions cannot always be expressed as primitive functions, as I said, cosines, tans, exponentials and coshes. So, for example, if you try in the workshop or yourselves using SymPy, the innocent looking integrals, and you'll probably find different difficulties with them. What they'll probably do is describe these as other functions that you've not seen before, you're not familiar with, that you'll have to look up, or alternatively it'll just say can't evaluate that particular integral. There's no way of expressing that using these primitive functions. So this is the idea of the notion of a primitive, and if we say something has no primitive, it means that we can't find an antiderivative in which it describes the integral. So now just a motivational example. We're going to let the pressure field behind a piston be defined by the so-called Gaussian function, where P of V is equal to e to the minus v squared, v being the specific volume of the gas behind the piston. And this is quite typical of when doing any type of modelling, piston type modelling within engines. The so-called specific thermodynamic work, which is also called the quasi-static work, is simply defined as P, the integral of P dV between the original and final volume. And in this case, we're going to just simply assume that V is equal to 1 and V of the original volume is equal to 1 and the final volume equal to 2. Setting that up in SymPy is relatively straightforward. First of all, we import the required functions, the exponential, and as before, we would need to also import the symbols and integral. We'll set the object V equal to the symbolic object of V. A little bit counterintuitive, but we have to remember that first of all, it set it up as a symbolic object, and the equals symbol within Python just put something equal to an object. We have to tell it what that type of object is, whether it's a numpy array or an integer or a float, and that's all that's going on here. Also, the function symbols does allow you to do multiple declarations of symbols. So if we had a U here, we'd have another space with a U there to define two symbols at once, as it were. Integral as before. We have the exponential. Could have used the double asterisk operator to raise to the power 2, but instead I've used v minus v times v to invoke v squared, and so this is minus v times v, and then the integral operator needs a tuple. The tuple is what it's integrating with respect to, in this case v, and then the limits of integration. So it needs a 3-tuple, and I've asked it simply to do it. Use the do it method on the integral operator. So this is the integral class, and in that class I've asked the method do it, and it's computed out the pi over 2, the error function at 2 minus pi over 2 the error function at 1. Question then arises, I guess, is what the heck is the error function? More about that momentarily. What we'd like to do is get floating point equivalents of this, and this can be found by the eval_f command within SymPy. So now we've just got it. We'll import the error function, the square root, and the pi from SymPy, and then we'd say compute this, which is obviously the error function at 2 multiplied by the square root of pi divided by 2, and then I'm taking off the other one, and then put this into brackets, and then said use on these objects, use the method evaluate function to 6 decimal places. An alternative method is just simply to use the special functions within SciPy, within Skippy, and of course using NumPy as well for the square root business. So we would have here, actually we could just use square root as well. It is available in SciPy and available in NumPy. I've used the NumPy equivalent here just to remind you on how to do that. Both of these methods would render a value of 0.13526 to 6 decimal places, so to 5 decimal places. So this leads us on to the notion of integral functions, and to do this we're going to go back to those rather innocent looking integrals from a couple of slides ago, and from SymPy I'm going to import symbols and integral, and also the exponential at the sine and the square root. I'm setting up x and n, but this time in symbols I'm setting n, and I'm setting the integer as true. So this particular case I'm using, rather than defining x and n in the same command, now setting up n as an integer, so when it performs its computations within the SymPy, within the Python language, it will indeed invoke n as an integer. I've then asked it to compute these three integrals below, and if you use Maxima or SciPy to do it, then you should render these results. And then if you looked up what the gamma function was, what the little gamma function is, in the SciPy help, you will find that they are these two functions, and are defined by integrals. One an improper integral, and one a proper integral so long as x is below infinity. It's as long as x is finite, I guess. The error function is again defined by this integral from 0 to x 2 divided by pi, and that can be seen directly from this. Of course, there's been a change of variables, and then this one is a very innocent looking one that we can't find as well. It's related to the perimeter of an ellipse, and so therefore it's called an elliptical integral. I think of the second kind. x6, and that the 6 is to do with this, of course. But again, the integral between 0 and x on this is also known as a integral function. So these particular functions cannot be described in terms of the primitive functions that we defined earlier, and therefore require numerical methods in which to evaluate these, and hence the focus of this week's video lecture and subsequent coding seminars.